how should governments, banks, and enterprise around the globe be truly responding to this impending quantum computing threat?
Yeah, they should be. Well, first of all, they should be aware that this is coming, and this is coming quite soon. I would say certainly within 10 years or so, we will see quantum computers that will be able to break sort of the encryption scheme that we have around now, RSA 2048. That is something that's being used, and that I think will be broken within 10 years. What banks and other entities that use encryption need to do is to move away from that type of encryption and go to this post-quantum encryption or look at this quantum mechanical solutions.
What the world is going to look like in the next 10 years, when we have like a truly working quantum computer.
I believe that with a quantum computer, we can do a similar thing. We have now a computational microscope that can compute further and better than what we can compute with our classical computer. And we will be able to see things that we couldn't see before or couldn't compute before. What we will see, we don't know yet what it is. Just like Van Leeuwenhoek didn't know what he was going to see under his microscope. And to his bewilderment, he discovered microorganisms and the birth of microbiology. I truly believe that we will see a similar thing with quantum computers.
Thank you for joining Once Changing the World. I'm your host, Eddie Avil, and today I'm delighted and honored to have with me Professor Harry Buhrman, a computer scientist, quantum computing pioneer, and currently the chief scientist, quantum algorithms and innovation at Quantinuum. Previously, he was professor of algorithms, complexity theory, and quantum computing at the University of Amsterdam, a group leader of the quantum computing group at the Centrum Wiskunde and Informatica, and executive director of QSoft, the Dutch Research Center for Quantum Software. Professor Buhrman research interests are on quantum computing, quantum information, quantum cryptography, computational complexity theory, Kolmogorov complexity, and computational biology. So, Professor, really appreciate you taking time and being part of the podcast. Wanted to start with the differentiation between a classical versus a quantum computer, because the computers, it's completely changed the world. From 1960s till right now, from mainframes to these large computers. Right now, we have a computer in a pocket, and it's completely upended society. And now I think we're at the cusp of this transition, which we might enter the quantum computing realm, though not for everything, maybe for narrow specific purposes. But will be great if you could, give my audience the difference between a classical versus a quantum computer, which actually kind of leverages the source code of life, the atoms.
Yeah, so that's that's sort of the basic question that we are looking at in the field of quantum computing. Let me tell you that classical computing has been going on for a long time. You could even say that it started thousands of years ago with, for example, the abacus, and it goes on with our current technology, with our laptops, and even our supercomputers like El Capitan, which is the biggest one currently hosted in the US. And all this technology is based on the same principle of information, the same fundamental principle, and that it's based on bits. And bits are the basic building block of these devices, and they are either 0 or 1. And someone who has sort of ventured into the field of computing knows this very well. Now, very recently, a new kit appeared on the block called the quantum computing, and the quantum computer is based on quantum bits, or qubits, as we call them. And these qubits, they are fundamentally different from the classical bits. They can be, in some sense, 0 and 1 at the same time, as opposed to either 0 or 1, which is the case for the classical ones. And these computers, they require completely new building blocks to be built, fundamentally different hardware. But maybe more importantly, at least for me, they also require fundamentally different software and software approaches. So it's not at all the case that the software that runs on your classical computers, I call them classical, but that's the ones we have around, that actually also runs on a quantum computer. you need to make use of new ideas that are given to you by this new hardware. And what is this fundamentally different part that is around in quantum computers? And that is that they are based on the laws of quantum mechanics or quantum physics. And this is the law, the study of nature in very small, at very small scale. And it turns out that nature behaves quite differently when you start to look at atoms and electrons, and that the laws that govern that world are called quantum physics, and they were only discovered or written down about 100 years ago by illustrious people like Einstein and Bohr and Schrödinger, and only sort of nowadays we're starting to understand how to make use of them for computation.
Right. These classical computers, they are completely upended our society, the way that can do. I think everybody, almost the entire world, has like got like a computer in their pocket and in the forms of mobiles, and here we are at the cusp of possibly maybe through that same paradigm, with bits, zeros and ones, we are standing at the cusp of possibly maybe building general purpose machines, possibly machines that are maybe have the same intellectual capabilities as us humans, though that we are still not close, but they say that with this paradigm itself we are maybe somewhere close to kind of build general purpose machines. And then you mentioned, right now we are going further and playing around with the source code of life, because you mentioned that universe is quantum mechanical, and Professor Richard Feynman has said nature is in classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. So, Professor, will be great if you could kind of distinguish between this bits and qubits. You kind of gave an overview of bits and qubits, but how is this information coded in the qubits? Will be great if you can talk about that. Are these bits? I mean, the qubits that you're talking about, is the information being encoded in the atoms itself?
Yes, it is encoded in a physical system, but that's the case also for classical computers, right? It's also the bits are also encoded in a physical entity. Maybe some current or no current is a zero or a one, and you need silicon and all that. So that's not really there's no real difference between classical computing and quantum computing, that they need a physical layer or carrier to store the information. The difference between quantum and classical is that these quantum bits, they can also store bits in superposition. So the quantum bit can be 0 and 1 at the same time. And there's a fantastic precise mathematical formalism that describes what a qubit is. It's just for those who care, it's linear algebra. It's a vector in a vector space called the Hilbert space. But I won't dwell into that. But the point I want to make is that there is a very precise mathematical description and framework that tells us what quantum mechanics is. So that's the theory. And then on the other hand, in practice, we can actually test this theory in reality, and we can build or try to build qubits that are both 0 and 1 at the same time, or can have this superposition. And up till now, all the experiments that have been done show that indeed this theory of quantum mechanics is correct, and that all the predictions made by quantum mechanics actually also hold in real life. So these things can be built, and in some sense, any two-level systems that can distinguish a 0 from a 1 can encode a qubit. And then if you can actually manipulate it in a quantum mechanical way, then you have a qubit in your hands. So that's in a nutshell what it is. You have this superposition principle, which is different from classical physics, right? You never encounter something in say at two places at the same time, but quantum mechanically this is perfectly possible. But the strange thing is, now when you start to look at such a system, look, when you measure a qubit, which is say in an equal superposition of 0 and 1, then what do you see? Well, you don't see a superposition. You actually, it's quite disappointing. You just see a 0 or a 1, just like in the classical case. But there is a slight difference. The difference is that now you see the 0 or the 1 with a certain probability. And this probability is proportional to how much of the 0 and the 1 you had in the superposition. And another strange thing is that once you look at this qubit and you measure it, then quantum mechanics tells you that it is destroyed, that it is collapsed. And the qubit now actually, if you saw a 0, is a 0 and it's a classical 0. So you lost all the sort of the magic from quantum mechanics that was around. So that's one thing. So you can measure these qubits and you can have them in superposition. By the way, it also means that you cannot clone or copy quantum information. Classical information can be copied perfectly, but quantum information cannot be copied. And this is, on one hand, a bit of a problem when you devise quantum algorithms. Sometimes you do want to copy information, but you can't simply. So that's the theorem. On the other hand, it can actually help when you try to make quantum cryptographic systems. Then it may actually help that you cannot copy information, because that then guarantees some security. We may be touching upon that a little bit later in this podcast. So then there is a second ingredient to quantum mechanics that's important for quantum computation, and that's the notion of interference. And interference is something we all know. For example, when you have noise canceling headphones, these headphones, they sort of make it that the noise that comes from outside and wants to enter your ear is sort of encountered with sort of an anti-noise that cancels the noise that comes in, and that allows you to listen to your music without being disturbed by the hum of an airplane, for example. Well, the same interference can be used in a quantum mechanical way, and it allows you to have these states that are in superposition to interfere with themselves, and in such a sense that they can positively or negatively interfere. And it turns out to be very important when you program a quantum computer, because the beauty is, and allow me to continue a little bit, sort of to make this slightly more clear. So when you have one qubit, it can be in a superposition of two states, namely 0 and 1. And each time you add a qubit, you double the number of possibilities. So when you have 2 qubits, it can be in a superposition of 4 different states. And so you see this exponential growth happening whenever you add a qubit into the mix. Note, by the way, that classically you would also have an exponential growth, because you will have an exponential number of classical states that the system can be in. But in the classical case, it will be in one of the 4 states. It will be either 0, 0, 0, 1, 1, 0, or 1, 1. Quantum mechanically, though, it can be in a superposition of all 4. So that's the difference between classical and quantum, as I said. And this also holds when you add extra qubits to the mix. And now each time you add a qubit, you double the number of possibilities that you can have in your superposition. So with 3, it's 8, and with 4, it's 16, and so on. So it doubles. And when you have a mere 300 qubits at your disposal, you have 2 to the 300 different states that your state can be in superposition. And now comes the sort of the beautiful idea of quantum computing, and that is that on each of these 2 to the 300 states, you can do a computation, and you can do that computation in parallel. So that is sort of mind-boggling, because 2 to the 300 is much bigger than all the atoms that we have in the known universe. So this is really an astronomically large number, and so you can do that many computations at the same time. Now, this sounds wonderful, and it is also wonderful, but the problem is that how are you going to get the information out of that huge superposition of computations? And now I already told you that if you look at a qubit, or if you look at multiple qubits, the system collapses into a classical state. And unfortunately, when you just do that, you will just see a random computation out of these 2 to the 300. And that is something that you could have already done without all this quantum magic. You just flipped a few random coins and you could do a random computation without all this. So what is the way out? And this is why I wanted to continue a little bit. The way out is to use this notion of interference. And when you use this in the right way, you can interfere this huge superposition of computations in such a way that the computation that actually carries the information or carries the answer that you're interested in, it sort of gets amplified, whereas the computations that carry information or calculations that you're not interested in get interfered in a negative way and you don't see them. And when you do this right, for certain problems, you can actually achieve an exponential speed up. But this is only for very specific problems. And for most problems, this is actually not at all the case. For most problems, a quantum computer is not going to be any faster than a classical computer. Actually, it will be slower, because quantum computers will be are slower than our classical computers. But for some problems, we have identified algorithms by using in a smart way this interference together with the superposition, so that we can do certain computations faster. But this is only for specific problems, and also you need very specific algorithms to do that. So it's not that you can speed up any algorithm on a quantum computer. That's not at all the case. You need a new way of designing your algorithms, and then you can do that.
Right, Professor, thank you so much for explaining it so beautifully. And you rightfully pointed out, it's strange, but it's super awesome. In fact, Richard Feynman, he has stated that nobody understands, quantum mechanics, because of this strange weirdness and awesomeness of the entanglement and the superposition. Uh, you said that, you mentioned that, the interference, helps over here. Now, I'm going to just kind of push that, because I just wanted to kind of understand the role of this superposition and entanglement. How do they contribute to the speed up? Because Hartmut Nevin, the head of Google Quantum AI, he had suggested that the speed of the Google's Willow quantum chip could be the evidence of the existence of parallel universe. He believes it must have borrowed computational power from these parallel universe to achieve this feat. David Deutsch is somebody else who kind of also endorses that view. So does Sean Carroll and Seth Lloyd and others. Are these uh, the superposition and entanglement and quantum computing, the speed ups, are they like actually leveraging parallel universes or dimensions for this quantum speed?
Well, first of all, let me say one thing. We haven't actually talked yet about entanglement, which is a notion when you can sort of get correlations between two quantum systems that you cannot get classically. And in some sense, I mean, entanglement is present, but in order to talk about quantum algorithms and speedups, you don't have to think in terms of quantum entanglement. So that's one thing. Although it's useful sometimes and it's very intriguing and interesting, it's not strictly necessary to do that. And so I prefer to talk about superposition and interference alone as the causes for the speedup. And now you talked about something else, and that is kind of interesting. You talked about this parallel universes, or the multiple worlds interpretation of quantum mechanics. And it's exactly that. It's an interpretation of quantum mechanics. And allow me to explain a little bit how this works, because I think it's kind of a misconception in many ways. Um, and it's sort of, in order to understand it, we have to go back to how we do science and how we study nature and the world around us. And the way scientists do this is by means of what is called the scientific method. And it boils down to the following um, way of working, the following paradigm. And that paradigm is you do some observations of the world around you. For example, when you have a stone and you drop it, it falls to the ground. And you do an experiment like that, and you do some observations, and then you try to come up with a mathematical model that describes what you have observed, what you just have observed. And then, if you do it right, this model also predicts what will happen in other situations. For example, it will predict that if you have the stone and you have it at a higher, let it fall from a higher position, it will actually hit the ground a little bit faster from a lower position. And there's a beautiful mathematical model actually called classical mechanics that describes this. But my point is that this is how science works. You do observations, and then you distill a mathematical model that describes these observations, and then you keep on doing other observations, sort of to falsify this mathematical model that you have made. And with falsify, I mean that the mathematical model predicts one thing, whereas when you do the experiment, something else comes out. Now, when you have found such a situation, you have to change your mathematical model and you have to upgrade it to a newer model that actually also captures this new observations, and so on. So now new experiments start, and you start to look around in the world again, and up everything is fine until you find a situation when your model no longer predicts what you see. And this is what science is, and this is also how we got quantum mechanics after we got classical mechanics, right? When we looked at the world at a very small scale, it turned out that the classical mechanics no longer was predicting correctly what we saw, and a new amendment had to be made. And that is what quantum mechanics is. It's a mathematical model that, as far as we know, predicts the world inconsistently with our experiments. Now, it could very well be that tomorrow someone does an experiment that is sort of inconsistent with quantum mechanics, that falsifies it, and then we have to change it. But so far, that has not happened. Now, what you're talking about this multiple worlds interpretation or these parallel universes, that is a way for humans to try to understand or to explain to themselves what this mathematical model means. But in a way, this is not necessary when you make quantum algorithms or when you build quantum computers. You don't need this interpretation. It's just something that, of course, you wonder about, and you want to explain to yourself what this superposition principle means. And I already said, okay, it means that an atom can be at different positions at the same time. Well, that's an interpretation. All we really know is that we have a mathematical model that predicts exactly what happens when you do certain operations, and then you do a measurement, and then you find that this atom is with some probability at one position, at some other probability at the other position. So in a way, whether it taps into multiple words or not, that is just an interpretational question. And I really don't know. All I know is that we have this mathematical model, and that predicts exactly what we see, and it predicts that you can compute in a certain way.
Right. No, no, fair enough. I mean, let's just get down and just do the maths. Fair enough. Professor, there are quite a few quantum mechanics interpretations out there, from the Copenhagen interpretation to the Hugh-Everett and others. Is there a specific quantum mechanics interpretation that you kind of endorse and would love to learn more about? Why do you endorse for your preference for the same?
The problem with these interpretations is that all of them have something strange. For example, the multiple worlds interpretation says that you have multiple worlds that all live simultaneously. That feels a bit weird, right? Because we never observed that. Then the collapse interpretation is strange because it suggests that things collapse when we look at them, and how can that be? And there's all of the interpretations have something unpleasant about them when you look at that. They solve some unpleasantness of one interpretation, but then they introduce another one. And I think there's no interpretation, as far as I know, that sort of doesn't have any unpleasantness in it. The only thing that sort of works without sort of problems is this mathematical framework. And so I'm sort of using that as my interpretation. So meaning no interpretation, just follow the math and see where it leads, where it brings you.
Perfect. Professor, quantum computers, will be great if you could,
By the way,
yeah.
all the people who work in the field do exactly that, but they also have their own private sort of interpretation on the side. But when they do their everyday work, they actually use the math and compute with that.
No, no, fair enough, Professor. Professor, will be great if you could talk about quantum computers and the different types of quantum computers which are being developed today, and what are the key architectural differences, advantages, and challenges associated with each of these quantum computers.
I would say you have many different ways of building a quantum computer, many different physical systems that you can use to implement them. For example, you have photons, or at Quantinuum, we use ions to encode the qubits by encoding the zero in some ground state and a one in some excited state of the particular ion. And photons, you can put the zero and ones in polarization, for example. Um, there are neutral atoms that you can use to do computation, to encode qubits. But all of these systems, they require that you can have the superposition of the zero and the one in a coherent way. That's how it's called. So without disturbing it. And you can already anticipate that it is quite difficult to build these qubits that are um, sort of able to carry these superpositions, because as we already said, once you look at it, you destroy this superposition. That's what quantum mechanics tells you. And in a way, doing computation means that you have to look a little bit at these qubits. At least you have to manipulate them. And so there is some tension between, on the one hand, having the superposition coherent or alive for a long time. On the other hand, you want to sort of do calculations, computations on and with these qubits. And so, on one hand, to keep the system stable, you have to shield it from the environment, because the environment will measure, and you don't want it to measure, but the environment might measure the qubit for you and then destroy it. So you want to shield the qubit from the environment. But on the other hand, you want to be able to do operations on them. And so these two are sort of fighting with each other. And yeah, that is the difficulty in building a quantum computer for all of these systems. And so the race is on to build qubits that are stable for a long time, that you can manipulate. And if you manipulate them, you don't introduce too much error. And so this is what we do at Quantinuum. We have qubits that are stable for a very long time. Ions have that property. And in addition, we can also manipulate them with very little error on those qubits.
Right, Professor. I want to get into Continuum, but before that, wanted to kind of, maybe because in the course of the conversation, we were speaking about entanglement, but we didn't elaborate on that. It will be great if you could do that. And in the beginning of the year, there was a breakthrough which was announced by a Chinese team that achieved the world's first 10,000-kilometer hack-proof quantum secured communication. Would love your thoughts on the breakthrough, and it will be great if you could also explain your work on quantum fingerprinting and its impact on secure communication.
Yeah, so now we actually venture into the realm of cryptography, and secure communication and secure quantum communication. And but before that, let me let's talk a little bit about what can you do with a quantum computer, because we really didn't talk about that. And so sort of the field gained a lot of momentum when Peter Shor in the early 90s showed that you can factor big numbers into their prime factors using a quantum computer. So, for example, 15 is 3 times 5. But when you get bigger numbers, it becomes actually quite difficult to factor a number. And actually, we don't know any fast classical algorithm that does that. But Peter Shor showed that on a quantum computer, you can actually factor large numbers in an efficient way. And this is very important because a lot of our current day cryptography actually is secure because we don't know how to factor large numbers. And so when you have a quantum computer that can factor efficiently, a lot of cryptography is actually broken. And so you need to do something to remedy the situation. And one way of doing that is by using quantum mechanics itself, sort of fight quantum mechanics with quantum mechanics, and use quantum mechanics to do communication called quantum communication between two parties. And actually, there is a beautiful scheme developed by Bennett and Brazar called the BB84 scheme, which was actually developed in 84, so well before Shor broke classical cryptography. And that scheme allows you to send a message from Alice to Bob. They're usually called Alice and Bob, using quantum communication. And the idea is that first you try to establish a secret key between Alice and Bob, so a random secret key that only Alice and Bob know. And they showed that their protocol can do that. And here comes the interesting part of quantum mechanics. The reason why it is secure is that when you send a qubit from Alice to Bob and somebody listens in the middle, called an eavesdropper, then that eavesdropper either gets no information on what is encoded in the qubit, or if she tries to get information, she has to destroy or collapse the state. And this can then be discovered by Alice and Bob. So they can sort of try again until they know for sure, or almost for sure, that nobody has listened in. And then they also are sure that they have a secret key, which they can then use to encrypt the message to send to each other. So this uh, key distribution, quantum key distribution scheme, is something that allows you to send messages from A to B. By the way, it doesn't solve all the problem that is surrounding cryptography, that's called asymmetric cryptography, that is broken by Shor's algorithm. So this public key cryptography is broken, and we need to find new ways of solving that situation. And by the way, that field, the whole field that tries to do this, is called quantum safe cryptography, or post-quantum cryptography. I already told you that you can have quantum communication to somehow remedy or save some of that. But also there's a lot of work going into new encryption schemes that are completely classical, that don't require a quantum computer, that are secure even against the quantum computer. But of course, they have the problem that tomorrow there might be someone who comes up with a new quantum algorithm that breaks these schemes. And by the way, this is not the case for the BB84 scheme, because that just is secure based on the laws of quantum mechanics.
Right. So current quantum computers, they are still far away from being commercial ready. And I think the largest problem over here there is, having error-free quantum computing. How far are we from achieving like a scalable, error-free quantum computing? And what fundamental breakthroughs, still, stand in the way of like an error-free quantum computer?
Well, first of all, let me correct you. We already have commercially available quantum computers in the world. Quantinuum is one company that actually sells them, but we're not the only one. There's many other companies that do that. So they are available, and they are getting actually quite interesting because we are now in a realm that these quantum computers have um, more than 50 qubits available. And the interesting part is that when you have more than 50 qubits available, it becomes very difficult to simulate these quantum computers classically. And so they are able to perform calculations that you cannot do classically anymore. The first examples of that were the demonstrations of quantum supremacy or quantum advantage, and these were just problems that are very difficult to do classically, but can be done quantumly, but may not be very useful. We're now actually seeing somewhat useful problems being computed on a quantum computer that cannot be computed classically anymore. Notably, there was a paper by people from Quantinuum out a couple of months ago that showed that a notion called quantum magnetism can be computed on a quantum computer. And we also were very careful, and we've thought very hard sought very hard to find classical methods to calculate the properties of these materials, and we were unable to do so. So I would say that the first examples of useful quantum advantage are showing up as we speak. But your question was, when do we have error free? And that's something I also want to say something about, and that is, I don't think we will ever have error-free quantum computers available, but what we will have is computers that have low enough error so that you can do the computation that you want to do on this computer. Let me elaborate a little bit on that. When you have a quantum computer that has error, say 1 in 10 to the 3, so 1 in 1,000, when you do your gate operations, then that means that you can do roughly about 1,000 gates, and before you will actually see one error. So you can do a 1,000 gates, in some sense error-free, but that's not entirely error-free, but with high probability that calculation has succeeded without error. Now, when you want to do a longer calculation, you need a smaller error on your gates. When you want to do 10,000 gates, you need the 2-qubit gate error to be 1 in 10,000. Otherwise, your calculation will return something that almost surely has an error or has multiple errors. So now physically, with the sort of physical qubits, we are able to bring down the error of our 2-qubit gates and the 1-qubit gates to 10 to the minus 3 or even smaller, almost 10 to the minus 4. So that means that without anything extra, you can do about 1,000 to 10,000 gates. Now, there is a beautiful field called error correction and fault-tolerant computation, by the way, also pioneered by Peter Shor, who devised this factoring algorithm, that sort of gives you a software solution for this problem of having very small error on your gates. And the way it works is that you can use multiple of these noisy qubits together to encode for a lower error, and sometimes people call this logical qubit. But this logical qubit still has an error on it, though it's a smaller error than you had on the physical qubits. And so this technique has been demonstrated by already quite a few groups. Also at Quantinuum, we have shown that you can reduce the error by using these quantum error correction techniques. And moreover, it has been shown also that you can do calculations on these logical lower error qubits. And sort of that is what needs to be done for what is called fault-tolerant computation. And this is something that we will see more and more in the coming period, and we will see that will happen.
how exciting is that? So you're saying from here that there is no fundamental blocks for an error-free computing, and you're saying that you got like a commercial-ready quantum computer which is solving specific problems already. You mentioned about quantum magnetism. What are the most compelling near-term and far-term applications of quantum computation that excites you the most? And since your work is in computational biology also, do you envision quantum computing playing a role in computation biology and drug discovery processes?
First of all, I mean, I sort of think it's important to sort of see two phases of quantum computation that are going to or that are happening. And the first phase is that of scientific discovery. And I think we are smack in the middle of the scientific discovery phase where we have this machine and it's able to do calculations that we couldn't do before. And we're just playing with it, exploring what is possible, trying out the algorithms that we already came up with 10 or 20 years ago, and also coming up with new algorithms and see what they can do. This is sort of the exploration phase, the scientific exploration phase we're currently in. And then within a few years, maybe 5 or so, up to 10, you will see that we can make good use of what we've learned in this phase and apply it to industrial problems, and we will get industrial advantage, and this will also have economic advantage. And so now the question you asked is, what are the problems that you can solve with a quantum computer that you cannot actually solve in a classical computer? This is actually quite a difficult problem. Yeah, in itself, a difficult problem to answer. But we do have a few ideas. I already mentioned the factoring algorithm of Peter Shor that breaks cryptography, but you might say that's not a very useful one. There isn't a useful one, and that is if you want to simulate nature, for example, for discovering new materials or maybe discovering new medicines or understanding how biological processes work, uh, then you actually need a quantum computer to simulate these systems. They cannot be really very well simulated on a classical computer, at least some of them cannot, because they're quantum mechanical in nature and they have this exponential explosion inherent in these systems. And so a quantum computer is ideally suited for simulating these systems and sort of measure what kind of properties these materials have. And so this is one big block of applications, simulation of nature, meaning quantum mechanics, quantum physics, and quantum biology, where I foresee applications. For example, understanding how light interacts with biological systems. For example, light that comes into your eye, that sort of works with a small protein called retinol, and understanding exactly how that works and how the interaction between light and the protein is a quantum mechanical question, and quantum computers can help us understand better how that works. Another one is coming up with new materials. For example, one that has superconductivity at high temperatures. This means that you can send energy through a wire without losing anything. And so, for example, this would solve some of our energy problems. And sort of the list is sort of long of potential candidates here, and it's going to be an exciting time exploring and finding out where this quantum computer can be applied.
Awesome. How awesome is that? Now, Professor, Google and IBM had claimed quantum supremacy and quantum advantage. What do these terms truly signify in practical, measurable terms? For the non-expert, and beyond IBM's, I think the quantum volume metric. Are there other benchmarks to truly understand this quantum advancements?
Yeah. So, well, yes, so sort of several questions. So, the first is what is quantum advantage? And quantum advantage, in a very simple terms, is that a quantum computer can compute something, property of a material or something that you're interested in. So you have an input and an output, and it computes that for you in an efficient and fast way. Whereas all the known classical techniques fail to do that; they take too much time. That's what I would call quantum advantage. And this, of course, is kind of a little bit of a rat race, because if you say, here is a problem and I solved it efficiently on my quantum computer, then of course, it doesn't mean that there isn't a classical way of doing it, but only you don't know of a classical way. And it could be that someone comes up with one. And we think that there are problems for which that is not the case. So that's what quantum advantage is. And this is also something that over time will become clearer and clearer. So the first experiments of quantum advantage, they have been shown not to show quantum advantage, because we came up with good classical techniques to solve these problems. But then, of course, knowing this knowledge, you will come up with an even harder problem that you can solve on your quantum computer, for which these techniques don't work. And this is currently what's going on. So I think this is something that over time we will learn that we have found quantum advantage.
Right. And Professor, are there any benchmarks to evaluate these quantum advancements?
Yeah, so these benchmarks are in some sense important, because they allow you to say that your quantum computer that you're building is actually a good quantum computer. Whereas, for example, classically, you measure how good or how fast your machine is by saying how many operations per second it can do. And that then tells you more or less what you can compute with it. Now, in the quantum world, telling you how many qubits we have is not so interesting, because, as we already discussed, there may be errors on them, and you need to be able to suppress these errors. And this may take a lot of qubits to build one more stable qubit. And so, what you can ask, though, is, and I think this is what it should mean, is what can you compute with your computer? And this is where these benchmarks comes in. They tell you how much computation can you do with your qubits that you have available. And you may have a zillion qubits available to do a very small computation. Then that only shows you that you can, with your zillion qubits, do this small computation. And so one of these benchmarks is developed by IBM, called quantum volume. And that tells you how deep of a circuit with how many qubits can you compute in a sort of meaningful way. Um, it's a very technical definition, but it is a way of assessing how good the qubits in your computer are, and how much algorithmic power they have. And so there are several of these benchmarks around, but I think quantum volume is the one that has stood out the best. Also, it's important that sometimes you can come up with a benchmark that's good for your machine, that's not good for other machines, and sort of that's maybe not so interesting. You want a benchmark that sort of tells you really what is the algorithmic or the quantum algorithmic value of your machine. In the end, it will boil down to, what can you compute? Is there something interesting you can compute with your machine? That's the ultimate benchmark, I would say.
Right, completely. Professor, there's two like really well-known algorithms. I mean, you spoke about Shor's algorithm, and then there's Grover's. Are there any other algorithms out there which holds most promise for potential impact in the this coming decade, in the next for quantum computers?
Yeah, I would say that it's maybe not so fair to say there's only two or three algorithms out there, because that's not really how I see it, and I think is also not how you should see it. There are a bunch of algorithmic techniques or building blocks out there, like the Fourier transform is one, the quantum Fourier transform, prominently in Shor's algorithm. And then there's other techniques like quantum walks, which you can see in Grover's algorithm. And so are a handful of techniques that are available to us. And then with these techniques, you can build almost infinitely many new algorithms that solve problems that you want to solve. And this is also what happens in the classical world. Also, classically, we have a handful of techniques available to us in our algorithmic toolbox. And then when you want to solve a problem, you tap into your algorithmic toolbox, you look at what kind of primitives are the best ones to use in this particular case. And then you start to use them, amend them, change them, come up with some new tricks, and then that builds a new algorithm. Quantum mechanically, this is similar, although the tools are different. The toolbox contains different primitives, but we sort of operate in a similar way devising quantum algorithms this way. And so there are thousands of quantum algorithms available in this way. And that's what we're developing. That's what we're doing.
Right. Professor, would love, I mean, if you could elaborate on the work that you're doing at Quantinuums and these algorithms that you're developing and the quantum computer, the trapped ion approach that you're doing, the quantum charged coupled device architecture. Will be great if you could elaborate on the works and the advancements at Quantinuum.
Yeah, so I joined Quantinuum about almost 2 years ago. And before that, I have been working in academic world, as you already explained. Since the late 90s, I've been interested in quantum algorithms and quantum information. And I've seen the field explode to where it is now. And so about 2 years ago, I decided that it would be very interesting to see up close how this industry works, and also to see a little bit up close how quantum hardware is built. Because in academia, this is really not possible to do, because, well, in academia, they just don't have hardware that good. And I have not been disappointed joining Quantinuum, I have to say. The hardware is truly phenomenal, and it's sort of amazing what they can do with it. The hardware at Quantinuum is based on these trapped ions. So these are atoms, and you encode the qubit in a sort of a ground state and an excited state. And what they are able to do is to move these ions around in a trap. And then whenever you want to do an operation on these ions, say a 2-qubit gate, you bring these two ions together and you shine a laser on them, and then it's really magic. Then then the gate has happened, and this way we are able to do calculations, as I already alluded to, that are very hard, or if not impossible, to do classically. Yeah, so this field has growing uh, so much faster than I anticipated, certainly 20, 30 years ago. But even in the short time that I have been with Quantinuum, I've seen great progress. And I can see a little bit further than sort of the public can see. And I'm not allowed to say much about that, but I'm sort of very optimistic about where the field is heading, and what we can do with it. And in some sense, it is also a dream come true that I can, in my lifetime, play with these machines that only were theory when I started thinking about this.
Right. Yes. So exciting, and congratulations on the $600 million raise. I mean, uh, it's like, I mean, in the next few years, possibly, when these quantum computers eventually they become error free, the applications that would come out of it's I think we can't even fathom that, because those applications might completely change the world. Continuum also has like a bunch of products and solutions. Will be great if you could elaborate on that.
Yeah, so we have actually a random number generator that can be used in certain um, cases. And we also have a chemistry package called Inquanto that can be used and sort of works in combination with our quantum computer. And in addition to that, we have a bunch of projects that we run with our customers to develop and sort of make new algorithms and applications that run on our quantum computer. In addition, we have a whole team that was actually set up since I joined, and I helped setting that up. That's an AI team called the Generative Quantum AI. In some sense, that's not yet a project, but it's sort of a certainly will become a project in the near future, where we use the combination of the power of quantum computers together with that of AI in several ways. And this is truly interesting. What I find extremely interesting is that a quantum computer is able to produce data. We call it quantum data, but it is actually just classical data that comes from a quantum computer that can be used to train quantum AIs or LLM or classical AIs, sorry, or LLMs. And in this way, you can even get something that is better than the machines alone. So better that it's quantum alone, or better than classical AI alone. And I don't know exactly where this will end, but it is truly fascinating and interesting.
Right, Professor, do you think you'll be able to elaborate on this work of convergence of, quantum meets AI, AI meets quantum? the work
Yeah,
that
so
you're doing?
that's exactly what this team that we set up, this generative quantum AI. On one hand, AI can help make quantum computers better, for example, by coming up with better error correcting codes or coming up with better compilations or smaller circuits that run smoother on your quantum computer. That's one application of AI to quantum. Then I alluded to the other way around, where you use your quantum computer to produce data that you actually feed into your AI and use it to train it. So that way you can train your LLM in a way that was impossible before. And then there's sort of the ultimate goal where they sort of work in unison, and the AI, for example, suggests a quantum circuit to the quantum computer that can run it and tell you what the measurement data is that comes out of this quantum circuit, and then give that back to the AI, who then sort of comes up with a even smarter or better circuit for solving a particular case. For example, one thing that sort of fits this loop very well is finding ground states of Hamiltonians, and Hamiltonians are ways of describing a physical system, and finding the ground state of such physical system tells you what the properties are of that system. So this is something that is important in the application areas we discussed before in quantum chemistry and quantum material design.
Right. Professor, now almost all exponential technology stack, they are both loaded with pros as well as cons. Pros, it's completely upending our world. But if it's gone into the wrong hands, it can completely lead to an existential threat of sorts. Even today, with artificial intelligence, we are at the cusp of possibly building artificial general intelligence, or maybe killer robots. So you're worried about that. That one side AI is doing so much cool, then there's the other side that it can be like an existential threat, and it's for all technology stack, like nanotechnology. Eric Drexler says that you could create gray goo of sorts, and then with synthetic biology, there's a mirror life, and there's with virtual reality, there's a potential to trap us into simulated realities. As someone who's like deeply vested in quantum computing, is there something that keeps you awake at night? And do you think that there could be some unintended consequences or the dark sides of quantum computing that maybe worries you?
Yeah, that could certainly happen, and not keeps me awake at night, because that's not very healthy. But I do worry about these things. I do worry for mostly in the AI setting, because I do think that I'm truly amazed about the power of these LLMs and what they can do. And I sort of converse quite a lot with them, and I'm truly amazed by what I hear back. Although sometimes it's complete nonsense, but sometimes it isn't, and that's of course I think where you should look. Um, yes, I do think there could be negative consequences of this. I don't see them so much with quantum, but I mean, who knows? I mean, we have to be very careful, and I think we should be monitoring the situation very closely, and if possible, counter any adverse effects that quantum slash AI or quantum AI have. Um, yeah, this is certainly something we as humanity need to do, and we need to have responsible ways of using this technology. I absolutely agree with you there. Actually, in my previous life at the university, we had a whole project that was devoted to precisely this question. Um, to have like the ethical and societal impact of quantum computing. We were monitoring that, and seeing what kind of steps need to be taken to make sure that this is going into the right direction. This is absolutely important that we do that.
Right. Professor, some of the biggest companies in the world currently are developing quantum computers, right from the Microsofts, Amazon, Google, IBM, and there are startups also, the D-Waves, Rigetti's, Quantinuum. Uh, uh, are there specific work of peers that has excited you or caught your attention?
Oh yes. I mean, that absolutely. Many of my peers do fantastic work, and come up. I mean, I'm sort of having a keen eye on quantum algorithms and new quantum algorithms, in particular quantum algorithms that have this exponential potential, exponential advantage over classical algorithms. Yeah, some of these algorithms have been have come out that show that, and I think um, traditionally we have been looking at algorithms that perform very well in the worst case, so that on every instance of a particular length, they perform exponentially better. But unfortunately, for many problems, such algorithms probably don't exist. And so now we have to look a little bit sort of for a somewhat less grand algorithm and less grand applications where we find quantum algorithms that work for special cases, for special instances as well, but maybe not for the worst case or for all cases. And these quantum heuristics is something that I'm keen on looking, but I'm keen on developing, and we are actually developing at Quantinuum. But also the whole field is developing beautiful ideas along these ways.
Right. Professor, my last question to you. Will you be able to leave our audience with what the world is going to look like in the next 10 years? When we have like a truly working quantum computer, error-free quantum computer, and you've written an article, technical perspective by the end of the decade, we will deliver universal, fully fault-tolerant quantum computing. Would be great if you could elaborate on that roadmap.
Yeah, so I think we already are sort of well on our way of doing that, and we already have demonstrated all the pieces and also some together that can be done. Um, and what we will see in the years ahead is that we will get bigger and bigger quantum computers with more qubits, and these error correcting and fault tolerant techniques will show to work and will work. And with that, we will be able to run, and this is sort of from my perspective what it's all about. We will be able to run more complex quantum algorithms with more gates that can do deeper computations. And I don't know what will come out of that. I mean, we discussed some of these applications, but I'm pretty sure that there are applications that we don't know what they are, that they will come out. I like to compare it with the 17th century Antoni van Leeuwenhoek, who was a merchant in cloths who devised a microscope, and that microscope was 300 times better than what was around at the time. And what did he do with that microscope? He started to play with it and put all kinds of things under it and look at it. And among the things that he tried was a drop of water from the pond behind his house, clear, crystal clear water with nothing in it. But when he looked at that water under his microscope, he saw that it was chock full of little animals, which we now know are bacteria and algae and microorganisms, but they were unknown at that time. And nobody actually believed that there was anything in this clear drop of water until they actually looked in van Leeuwenhoek's microscope. And I believe that with a quantum computer, we can do a similar thing. We have now a computational microscope that can compute further and better than what we can compute with our classical computer. And we will be able to see things that we couldn't see before or couldn't compute before. And what we will see, we don't know yet what it is. Just like Van Leeuwenhoek didn't know what he was going to see under his microscope. And to his bewilderment, he discovered microorganisms and the birth of microbiology. I truly believe that we will see a similar thing with quantum computers. But I can't tell you what that is. Not because I'm not allowed, but because I don't know.
Thank you, Professor, for taking time and being part of the podcast. Such a profound note to end on. Yes, I think we are entering the world of the unknowns. The current computing paradigms, the zeros and ones, has upended our world. And like I said in the beginning of the conversation, we've got all have like a computer in a pocket, and we are at the cusp of building a machine that could be as intelligent or beyond us through that current paradigm, and that's classical computing with using zeros and ones. And here we are entering the world where we will be computing with atoms itself, because the world itself is quantum mechanical. And yes, it's got its weirdness, but I think once we truly get a fault tolerant, error free quantum computing, what can come out of it is going to be truly magical. It's going to be completely possibly change the world. Maybe diseases might not exist. Maybe we might live forever. Maybe we might find new materials. So very excited for that world. Wish you and everyone at the Continuum the very, very best. And to my listeners, if you like what you see and hear, then please press the subscribe button. Until next time, see you guys. Bye. Thank you, Professor. Really, really appreciate this. Thank you.
Thank you very much, and take care.